physical geology students. I hope everything's going good. This is the next lecture for July the 6th, and we're still on chapter number 9. It's quite a chapter, I tell you, because there's so much information that's included. You need to know about stress and strain, strike and dip. Hopefully you watched that video about strike and dip. And we learned about the different kinds of faults, different kinds of stresses. Watch this video twice, 3 times, whatever it takes, so you know the difference between the different types of faults and how to identify hang walls and footwalls. Let's start off over here at this diagram. What this diagram shows you is you got 3 curves here, and this is your famous bivariate diagram that scientists love so much, where you got 2 variables and you want to see how they relate to one another. On the x-axis you have strain, and as you go from left to right, strain increases, and as you go from the bottom up, stress increases. So you could tell that and you got 3 curves here: a green curve, a red curve, and a yellow curve. There's various things you can glean out of this particular diagram. The first is, when you increase stress on a rock, the strain in the rock goes up. In other words, the rock changes shape more with the more stress you put on it. Think about it. If you take a rock, you're going to need more stress to change its shape more. Now, notice that with all 3 of these curves, they start off with straight lines in each case. So at the beginning, when you add stress to a rock, it's going to strain in a linear way. That's what we call elastic deformation. So what is elastic deformation? Well, when you first apply stress to a rock, strain will increase linearly. Now to get rid of this thing here. Okay. Oops. Okay, I got to get my face back on here again, I guess. Oh, that sucks. All right, there we go. So think about it like this. Elastic deformation, when you first start to add stress to a rock, it starts to change its shape. But during elastic deformation, the change in shape of the rock is temporary. So that if you release the stress on the rock, the rock will return back to its original shape during elastic deformation. So elastic deformation, visualize a rubber band between my 2 thumbs. If I were to pull apart that rubber band, I'm putting stress on that rubber band, it's going to change its shape, right? As long as I don't pull it too far apart so it breaks, it's going to be able, once I release the stress, it's going to go back into its original shape. That's what elastic deformation is. And elastic deformation, represented by these 3 dashed lines for these 3 different rocks, is what causes earthquakes. I'll repeat that. Elastic deformation causes earthquakes. That when you cause rocks to change shape temporarily, and then you release that stress and the rock returns back to its original shape, you get an earthquake. Another way to get an earthquake is if you just flat out break the rock, which is what's shown here in red. If you put enough stress on a rock, it's going to break. Imagine a rock pillar like this. If I take a sledgehammer to it and I slam down on it, that's a huge amount of stress. That rock's just going to flat out break, and that's going to cause an earthquake as well. So earthquakes occurs by either rupturing the rock through a sudden application of stress, or through elastic deformation, where the rock temporarily changes shape due to the addition of stress, and then when it returns back to its original shape, then you get an earthquake. So both of those ways will work to make an earthquake. Now, what this yellow line and this green line are showing you for two different kinds of rocks is that once elastic deformation is over, then you're in this part away from the dashed line, and you can see that an increase in stress still causes strain to increase, but it's not linear. That's what we call plastic deformation. Plastic deformation is not the same thing as elastic deformation. Plastic deformation means that rock has permanently changed shape. It can't return back to its original shape. For example, if this stack of papers here represents a bed of sedimentary rock, and I were to push this rock together, and so that it doesn't return back to its original shape, then I will cause the rock to fold. Plastic deformation makes folds, not earthquakes. It causes the rock to permanently change shape. That's called plastic deformation, when the rock permanently changes shape. When I push this bed together, I compress this bed, I make folds. Next thing we're going to talk about is geologic maps. And soon we're going to have labs on maps. And there's two kinds of maps we're going to look at in physical geology. We're going to look at geological maps and topographic maps. Okay, so you need to, I don't know if you've ever worked with maps before, but we're gonna if you have worked with maps before, then this will be a lot easier for you. If you haven't worked with maps before, it might be a bit more difficult. Let's take a look at, first of all, what a topographic map is. Okay, this shows you a typical topographic map. And with all maps, ladies and gentlemen, from now on, remember, up is north, to the right is east, to the left is west, and down is south. So, which way is that then? That's northeast on a map, right? How about this? That's northwest. This direction, southeast. This direction, southwest, right? So we always got to remember directions. Which way are we going when we're looking at a map? All right. Now, so take a look at this map here. This is a topographic map. And notice the green here. If you have green like this, that means there's vegetation, trees or plants. So this is it's not bare ground here. It's covered by vegetation. If, on the other hand, if you have white, like over here, there's no vegetation here next to this river. Okay, but here you got vegetation. All right, now you're going to have brown lines on topographic maps. And these brown lines represent elevation above sea level. It means how high are you above sea level. In the United States, topographic maps are measured in feet. The rest of the world, it's in meters. So we're mostly going to, in this class, going to be working with topographic maps made in the United States, so they're in feet. But once in a while, we'll get a Canadian map, and don't forget that it'll be in meters instead of feet. So here's a brown line. How high above sea level are we on that brown line? We're 100 feet above sea level. See how that works? Right here, how high above sea level are we? We're 200 feet above sea level. 300 feet above sea level. So as we walk, if we were to walk from here to here, if we were to walk north, would we be from here to here? Are we walking uphill or downhill? We're walking uphill, right? We're walking uphill. This is a topographic map. Topographic maps are something we'll be talking about more later on. But now let me show you what a geologic map is. I'm going to show you the first geologic map ever made, and it was made in the United Kingdom, Great Britain, by the Royal Geological Society. It was made by William Smith, by the way. William Smith is the one who came up with the principle of fossil succession. So here you can see Britain, and Britain includes England, and north of here is Scotland, and Wales is over here, and Northern Ireland. That's the United Kingdom. Now, as you go from England to Scotland, are you going north? Yes. To get to Ireland, you need to go west, right? These colors here represent the rocks that you will see when you are at some particular location. For example, if you were here in Cornwall, right here, you would find this color, a greenish color. And then you would have to look over at the key for the map and see what color rocks do you have there. So, for example, in London here, you would have these Cenozoic rocks. Here in Nottingham, you'd be at late Paleozoic rocks. So what a geologic map shows you is what rocks are you going to find at any particular location. So usually they'll give a name for it, like this will be the Nottinghamshire shale, or this will be the Isle of Man limestone, or whatever. It doesn't matter where you are in the UK. You can find where you are on that map, and then you can look over at the key, and you will know what rocks you'll find there. That's called a geologic map. We're going to be working a lot with geologic maps. In order to understand how to read a geologic map, we must understand that symbol, strike and dip. Strike and dip. This is a strike and dip symbol, and you'll see strike and dip symbols on these geologic maps. The strike is the longer line, and it's always measured from north. So in this particular case, the strike of here depicted is about north 20 degrees east. It's 20 degrees from north, so it's north 20 degrees east. The dip in this would be southeast at 45 degrees. Here you can see strike and dip for two sedimentary beds. The strike is this direction here, represented by this plane, and the dip is this. It follows the tilt of the beds, and in this case it would be about 45 degrees to the east. The east is to the right. Next thing we're going to learn about is, remember when I talked about plastic deformation a moment ago? Plastic deformation means when rocks permanently change shape. Well, remember I made a fold by pushing the rocks together, compressing them? So you got two main kinds of folds here, ladies and gentlemen. Okay, let's imagine for a moment that we have bed 1 represented by this piece of paper. And you can do this at home if you wanted. Bed 2, and it was deposited on top of bed 1. And then bed 3 is deposited on top of bed 2. So you got 3 beds, and they're flat. They're horizontal. Sedimentary beds are originally deposited horizontal, so they're like this. 3 horizontal beds. If I push these rocks together, causing a permanent change in shape, I make a fold. There's 2 main kinds of folds. If this kind of fold that I have in my hand right here is an anticline. Here you can see 1, 2, 3, 4 beds, and you compress them, you compressive stress here, you made an anticline. This is called an anticline. However, there's another way to do it. Let's say I push the rocks together and they do this instead. That is a syncline. So let's take a look at some pictures here. Anticline versus syncline. This is an anticline. This isn't. Okay, this is underground. Here's on top, right? This is called a block diagram. This is an anticline. This is a block diagram showing an anticline. This is a block diagram showing you a syncline. I've just made an anticline and a syncline. Which one is the anticline? Is this one here the anticline? Yes. So this one here must be the syncline. How many anticlines do I have here? I've got 2 anticlines and 1 syncline. Let's look at this block diagram here. How many anticlines do you have? 1, 2, 3. And you've got 2 synclines. 1, 2. But notice that this has been, the top of the anticlines have been eroded away, right? So you can't see the anticline and the syncline on the surface of the earth here because they've been eroded away. So how can you tell where the anticlines and synclines? Okay, imagine you're a geologist and you go here and you see this a shale here represented by this green rock and a sandstone here, and then a shale and a conglomerate and an arkose, and then you see repeating patterns of stripes like this. If you see repeating patterns of stripes like that, even though you can't see the anticlines and synclines above the earth, you know that they are underground. Why do we need to know that? Well, many reasons. First reason is an anticline is the best place to find oil and natural gas. That's what geology is about, making money. Oil and natural gas accumulates on the inside of anticlines, especially in Tennessee. Ever had an oil and natural gas company approach you when you bought a piece of property? They know where the anticlines are, and they're going to your property, and they're going to try and negotiate a deal. Some people get monthly checks. You have an oil rig or a natural gas rig on your property. Make sure you get a lawyer first, because they'll try and cheat you mostly. They'll try and get as much out of you as possible if you don't know what you're doing. But know where these, if you see stripes of rock that repeat themselves, see how this green rock repeats itself? It's the same rock. When you have patterns like that, you know you're looking at anticlines and synclines. Did I have to push the rocks together or pull them apart to make anticlines and synclines, which are the two types of folds that we've been talking about? I had to push them together, right? So where are you going to get anticlines and synclines? At convergent or divergent plate boundaries? At convergent plate boundaries, where you push rocks together, that's where you're going to get anticlines and synclines. We have anticlines and synclines in Tennessee. So Tennessee was an ancient convergent plate boundary then, right? Formed by compressional stress. Let's take a look at a picture here. I'm going to try and draw a picture of this. I'm not too good at using this app, but I will start. I'll try. So let's say you have bed 1. You got bed 2. I'm trying to draw straight lines, but I can't do it. And you got bed 3. Okay, now put a little tree here, so you know that's the surface of the earth, and there's a bird. So this is underground. Which bed is oldest? Bed 1 is oldest, and bed 3 is the youngest, right? Okay, now let's say I push these 3 beds together using compressional stress at a convergent plate boundary. Then I'm going to make folds if plastic deformation occurs. So that, wouldn't it look like this then? Wouldn't it look like this after I compress these rocks? How many anticlines do I have here? 1, 2, and I got a syncline over here. And now the next part's a little tricky. Try and follow me here. First, I'm going to erase this because to give me some space. Now, ladies and gentlemen, because there's 2, bed 3, right? Here's bed 2, and here's bed 3. 2 anticlines and 2 synclines. Okay, now if the rocks are folded like this and they haven't been eroded, then it's easy to tell that that's the anticline, and that's a syncline, and that's an anticline, right? But life is not so easy. Most of the time, erosion occurs. So let's say I eroded these rocks. I'm eroding these rocks now. Over time, rocks wear down. They break down through erosion. Now the land is basically flat. Right? So this is the ground. I'll put a dog here so you know. There's a dog. And here's his tail. There's a bird up here. The dog's taking crap right here. I'm sorry, it's not funny. But anyway, you understand the ground is flat. I'm having fun doing this. Anyway, I can make a block diagram out of this by going like this. So I'll make this a block. This is called a block diagram. Obviously the lines are straight, but I can't do it with this app here. But I think you see this is now a block. Now this is what we see on the surface of the Earth here. And this is at 90 degrees. Okay? So what are we going to see in the real world when the rocks have been eroded then? We're going to see stripes of rock that repeat themselves, aren't we? Like this. These should be straight lines. I can't draw a straight line with this app, but I think you get the idea. So this would be bed 3 here. That would be bed 2. That would be bed 1. Bed 2 here. Bed 3. Bed 2. Oops, hang on. I forgot. I didn't draw this line in here. Okay, so let's go on bed 2, bed 1, bed 2, bed 3, and over here what would we see on this side of the block? Bed 3, right? But everything here on this top part is what we would actually see. If you're a geologist, you would see, oh, I see bed 3, bed 2, then 1, and then I see bed 2 again. And then I see bed 3, then I see 2 again. I see 1 again, then I see 2 and 3. And geologists are not confused by that, because when you see these layers appear again when you're walking, you know that you've got an anticline or a syncline beneath the ground. You know you have folds underground. This right here, is it a syncline or an anticline here? That's a syncline. And from now on, we need to remember that this symbol means that you're at the center of a syncline. So that symbol means you're at the center of a syncline. And the geologist will put that on the top here so that on your map, your geologic map is this top part of the block diagram. So people know that right under here is the center of the syncline. The center of the anticlines, where were they? They were right here. And this symbol here represents an anticline. That means anticline. That means syncline. Okay? So, what about this? What is this? That wasn't the center of an anticline. Okay? So, when you see these symbols, know what they mean. Syncline, center of synclines here, center of anticlines here, center of anticline here. Then you also need to know what the strikes and dips of the different beds. So here's bed 3, right? Remember, this way is north. So that means this way is east, this way is west, and this way is south. All right? Now, I'm going to draw in the strike for bed 3 and the dip. The strike for bed 3 will be this. Remember, the strike follows the bedding planes. So here's a bedding plane between bed 2 and 3. It must be parallel to that. And the dip is at 90 degrees, but it is bed 3 dipping to the east or to the west? It's dipping to this way, to the east. And the angle, the deviation from horizontal, is about 70 degrees, and I could draw that in. What's the strike of this bed, bed 2? It's the same as for bed 3, because all of these bedding planes are parallel, and then you put the dip in. How about the strike for bed 2 over here? It's like this, right? How about right for bed 2 over here? It's like this. So you got to put the strike and dip symbols in if you don't have one of these in, anticline or syncline symbols. There's the strike and dip of bed 2 over here. Here's the strike and dip of bed 3 over here. So what is your job, ladies and gentlemen? Your job as a geologist is you're going to get this part here, and you're going to have to fill in all this stuff down here. You're going to get this up here, and you're going to fill in this stuff down here. Like you're Superman and you have X-ray vision. You could see underground. How are you going to do it? Well, it's easy. Okay, this is the center of a syncline. As you walk toward, remember, bed 3 is the youngest, bed 1 is the oldest. As you walk towards the center of a syncline, do rocks become younger or older? They become younger, right? So we know that's a syncline. Even if I didn't have these strike and dip symbols, I would still know that this must be the center of the syncline because the youngest rocks are in the center of a syncline. As you walk towards the center of an anticline, do the rocks become older or younger? They become older. So that must be an anticline right here because the oldest rock is in the center, and that is one over here because the oldest rock is in the center. Now let's say we didn't have these numbers here. We didn't know the ages. How would we know, are we dealing with a syncline or anticline? Well, here's an anticline. How do I know? Because the rocks on both sides of an anticline dip away from the oldest layer. Do the rocks on both sides of a syncline dip towards the center of the syncline? Yes. And they dip away from the center of an anticline. Okay, so let's test our knowledge here. Let's test our knowledge here. No, I'm going to just get a new one here. Okay, now let me ask you a question here. If you're looking at a geologic map, I'm going to do some real simple stuff here and see if you can get it. And I know you can do it because you're smart people. Let's say you see the following sedimentary beds on your geologic map. And the youngest rock is in the center, bed 3. And then you got older rocks on both sides and even older rocks represented by the number 1 farther away from the youngest rocks. As you walk towards the center here, are the rocks getting younger or older? They're getting younger. So you should immediately know that this must be a syncline. And to show that you know that, you draw this symbol in. Okay, I'm going to tell you a joke while I'm doing this, and I hope nobody gets offended. Um, it's a Polish joke, and my my army buddy Arthur Pachowski, one of my best friends, is Polish, and he doesn't mind. He thinks these jokes are funny, and here it goes. Um, have you heard about the Polish family that froze to death uh, at the outdoor movie theater? They were waiting for the movie closed. They were waiting for the movie closed for the winter. All right, it's not funny. Okay, so here we go. Let's say that we have instead no ages, but we just have strike and dip symbols. Here's your geologic map, and and somebody is taking a strike and dip of these, so you know that here. By the way, are the strikes the same for all of these beds? Yes, they're all the same. They're parallel on both sides. But is this an anticline or syncline? The beds are dipping away from the center. Is this an anticline or syncline? Tell me the answer. You should know that this is an anticline. And to show that you know it, you draw in this symbol. So, if you were to go underground, what you would see is this, an anticline. So you could go ahead and put in numbers. So you show that this is the oldest rock, and this, and as you go away from the center, the rocks become younger. You can put the numbers up here so it make it clearer. Okay, very good. There's a third type of fold called a monocline. Okay, so we know what an anticline and a syncline are. Now we're going to try and figure out what a monocline is. Monocline. You know that the word mono means one, and in Latin, and cline means um, an inclined surface. So it has a monocline has one inclined surface. Another way of saying it is this is a monocline in a block diagram. Notice that from here to here, the beds are horizontal. But from here to here, the beds dip, in this case to the east. So monocline, the bottom line is this is an anticline. This is a syncline. A monocline looks like this, with you got flat rocks, and on one side they fold. The other side's horizontal. They're flat. Okay. Let's take a look at some more pictures. I wish I had a blackboard and I could just show you this stuff, or a whiteboard instead of doing this quarantine stuff, because it's hard to show. Okay, let me show you what okay, the symbol for horizontal beds real quick. Okay, so bottom line is, let's go back to our whiteboard here. So a monocline is going to look like this. That's a monocline. Let's make this into a block diagram. Now let's say I asked you to fill in these two white spaces. Could you do it? Well, you could if you knew what this symbol meant. Okay, here's another symbol we need to learn about. That symbol means horizontal beds, flat beds. Okay, we already learned about this symbol, strike and dip, and we learned that this symbol means anticline, the center of an anticline. This symbol means the center of the syncline. The next symbol is this, a bullseye, and it represents horizontal beds, flat beds. Are these beds flat from here to here? Yes. So this one's a little bit more tricky, but to draw in a monocline, you put in a dashed line to show you on which side the flat beds are and which side the inclined surface is. And you just told me that these are horizontal beds on this side, on the western side. So we'd go ahead and put a symbol here to show that. Now what else can we do here? Well, this is bed 3 here. And are these beds striking, or what's the strike of these beds? Well, the strike is going to follow that dashed line, and the dip is going to be to the east. That's how you draw in a monocline. So anticlines, synclines, and monoclines. We learned a little bit about those. That's a syncline, right? Can you tell that's a syncline? As soon as you see a syncline, you should go a step further and say, aha, that formed by plastic deformation from compressional stress at an ancient convergent plate boundary. The Appalachian Mountains are anticlines and synclines. They're folds formed by plastic deformation at an ancient convergent plate boundary. Also, don't forget, anticlines are the best places to find oil and natural gas. Because when you're in, next chapter is about mass wasting, and I bet you didn't know, but this class can help you make money in real estate. And the price of real estate is tied into the geology underground. That's why real estate investors always hire geologists. I know I've got friends here who invest in real estate in Anderson County, about 50 houses. They know the geology. You need to know the geology because it's going to affect the price of the real estate. And obviously, if you have an anticline on your property, you own the oil and natural gas rights, just as you own the water rights, which we'll talk about later on. So we talked about anticlines and synclines a bit. And one more thing before we get into domes and basins is we need to know what some terms here. So let me show you what these terms are. Anticline, syncline, axial plane. Okay. Here you have here's an anticline, here's a syncline, and here's an anticline. You can draw an imaginary plane straight through the center of each of these folds, and that's called an axial plane. For example, this anticline has an axial plane. Here's the axial plane of this syncline, and here's the axial plane of this anticline. So an axial plane is an imaginary plane that goes through the center of the folds. You got 3 axial planes in this diagram, right? So notice that all 3 of these axial planes are vertical. They're straight up and down. All the folds that we've talked about have had axial planes that are straight up and down. The axial plane for this anticline here is right here. It's straight up and down. So these are called upright folds. Upright folds have axial planes that are straight up and down. But think about it. Can't this anticline go like this, or like this, or like that, or like that? And in that case, wouldn't the axial plane not go straight up and down? This axial plane is going to go down like that through the paper, through the center of this anticline. And that's called a plunging anticline or a plunging syncline. So going back to our paper again, a plunging anticline or a plunging syncline. Okay, now this is what we see above the surface of the Earth on our geologic map, and this is underground. That's what we got to figure out. And we're making another black diagram. So we can still figure out that if this is an anticline or syncline. Remember, this is our geologic map, because if we have the ages of the rocks, as 1 is the oldest, 4 is the youngest. As you walk towards the center of this, you get to older rocks. So this must be a anticline. So then you can just fill this in. This is what it would look like underground. Right? So we can show that we know that this is an anticline. It's not straight lines like it was with the upright anticline, but we still know it's an anticline because we walk towards the center, it gets older. So we know what this is, and we put a symbol in to show it. That's a plunging anticline. Even though it's not straight lines we're dealing with, if it's curves, we know it's a plunging fold. It's either an anticline or syncline. We know that's a plunging anticline. Let's do a plunging syncline. Make our trusty block diagram. Your geologic map is the top. Now let's say we see this instead on our geologic map. And we see that the beds repeat again. So we know it's some kind of fold, but the bedding planes are not straight lines, so we know it's a plunging fold. As we walk towards the center of this thing, do the rocks become older or younger? Okay, let's say I gave you that, and I asked you to fill in all the information you can here on these blank spaces, and also put in the strike and dip symbols and anticline, syncline symbols. Could you do it? I give you this. I'm giving you this. I'm asking you first fill in the bottoms, the two blank sides, underground. Okay, you would know that first of all the rocks are younger in the center. So is this a plunging anticline or a plunging syncline? This must be a plunging syncline because the rocks become younger as you go towards the center. So then you can go fill this out. You know it's a syncline, so it's going to look like this. Just basic geometry, ladies and gentlemen. What else can you do here? Well, then you can do some strike and dips here. Remember, the strikes are parallel to these bedding planes. And is it dipping towards the center of this incline? Yes, beds always dip towards the center of the incline. So I draw that. Notice how I draw that one longer to show the strike, and this one shorter to draw the dip. Let's draw the strike and dip for number two, bed number 2. Let's draw the strike and dip for bed number 1 here. Bed 3 over here. Bed 2. And bed 1. Okay, so if I gave you just the top of this, you should be able to fill in this stuff down here, right? Okay, so now you know some symbols. That's the center of an anticline. That's the center of a syncline. That's a strike and dip symbol. Strike, dip. That's horizontal beds. And the next symbol you need to know is what's the cross. Not the cross, but the cross in geology, not in mass. Cross means vertical beds. It means going straight down like this. So let's say I had a block diagram. Remember, north is always that way. Okay. And let's say that there are 3 different beds. Beds 1, 2, and 3 different beds. And I had the symbol, the cross in the center. Your job now, tell me how to fill in these blank sides. How am I going to fill in those blank sides? Well, they're vertical beds because they've got these crosses in them. So then I know the answer, don't I? Wouldn't it look like this underground? Okay. I'm going to show you a few more things, then we'll move on. And then I'll call quits for now, but let me show you a few more things here. Going back to our faults, I wanted to show you some things about faults here that we talked about before. Let's say this is the ground. There's a tree right here. That's the surface of the earth. And there's a crack in the ground, which we call a joint. And we have 2 beds. Beds 1 and 2. And the crack, which we call a joint, the crack goes through beds 1 and 2. Which is older? Cross-cutting relationships tells us that the sedimentary beds are older because they're cut by the fault, right? Now let's say that this side moves up. Notice how I drew a half arrow like this? To show which side moves, we always draw half arrows, not arrows like that. Don't do that. And let's say that this side moves down. What's it going to look like if that happens? Won't it look like this? This is, okay, now to tell what kind of dip slip fault this is, imagine you put the base of your fist right here and found which side does your thumb point to? It would point to this side, right? So we know this is the hanging wall. And I'll write that in to show we know that. And therefore this must be the foot wall. If the hanging wall goes up, ladies and gentlemen, it's called a reverse fault. Okay. Now let me show you a normal fault. Same situation. We're going to have two beds, beds 1 and 2. And what this is the surface of the earth representing that by that tree and this bird. Okay, we got a crack in the rock called a joint. But this time we're going to have this side move down and this side move up. What's it going to look like if we do that? It's going to look different, won't it? It's going to look like this. And we'll draw in our half arrows to show that. Which is the hanging wall, this side or this wall? Put the base of your fist and point your thumb up. This is the hanging wall. So we'll draw that in to show we know that's a hanging wall, and that's a foot wall. If the hanging wall moves down like this, we call it a normal fault. Do you see the difference between the two? Now let's do right lateral, left lateral, strike slip faults. Okay, now we're just looking at the surface of the earth. So you're looking down from an airplane and you see a fault, and there's a road here. On one side of the fault, there's a road on the other side of the fault. Remember, this is looking from above. And we see the offset of this road. This road used to be the same road. This side must have moved like this after the earthquake, and that side must have moved like that, right? We'll know that's a strike slip fault. Now we want to figure out, is this a right lateral or left lateral strike slip fault? The way we figure it out is, let's say you are here at X. The earthquake occurs. The movement occurs. Which way did the road move on the other, looking on the other side of the fault? To your right or to your left? It moved to your right. So this is a right lateral strike slip fault. Let's have another fault here. And let's say we have a fence here, and we have a fence here. After the earthquake occurs, this side moved this way, and this side moved this way. You're standing here. Which side did the fence on the other side of the fault move? It moved to your left. So this is a left lateral strike slip fault. All right, I know it's a lot, but watch some videos online if it helps you. Look at the book. Watch some YouTube videos. Watch my videos. Know how to identify anticlines, synclines, vertical beds, horizontal beds, monoclines, plunging anticlines, plunging synclines, right, left lateral strike slip faults, normal faults, thrust faults, and reverse faults.